What challenges exist in proving system deadlock freedom? Imagine trying to prove that a busy intersection will never get stuck with cars blocking each other. That's similar to what proving deadlock freedom in computer systems involves. Deadlocks happen when processes wait forever for resources held by each other, causing the system to freeze. But showing that this will never happen is not simple at all. One big challenge is that it's often impossible to decide for every possible situation if a deadlock can occur. This is because of something called undecidability, which means no single algorithm can always tell you whether a system can deadlock or not. Another problem is the explosion of possible states the system can be in. Think of it like a huge maze with countless paths. As the number of processes and resources increases, the number of different ways they can interact grows exponentially. This makes checking every possible scenario practically impossible for larger systems. Then there's the tricky part of the system's behavior itself. When processes create new threads or resources dynamically, it becomes harder to model and predict all the interactions. Locks can be acquired and released in different orders, making it even more complex to analyze potential deadlocks. Detecting deadlocks by looking for cycles in resource dependency graphs can help, but it's not foolproof. Sometimes deadlocks happen in ways that don't show up as simple cycles, especially in systems that communicate asynchronously or are distributed across multiple computers. To prevent deadlocks from happening, many developers relying on design rules. For example, they might enforce a strict order for acquiring resources or use hierarchies to avoid circular waits. But applying these rules requires careful planning from the start, which isn't always easy. There's also a trade-off between how precise the verification is and how fast it runs. Highly accurate methods tend to be slow and don't work well for big systems. Faster methods might miss some deadlocks or flag false alarms. Formal verification tools can provide strong guarantees but often need experts to set up and can take a lot of time. They requiring modeling the system in a formal language, which can be a challenge for complex software. To tackle these issues, many teams use static analysis tools that look at lock patterns to find potential deadlocks early. They also adopt design practices like fixed lock orders and resource hierarchies to prevent circular dependencies. Runtime monitoring can catch deadlocks during operation, allowing the system to recover. Breaking large systems into smaller, well-understood parts helps too, as it makes verification more manageable. Using formal methods on critical components can give extra confidence that deadlocks won't happen there. Understanding these hurdles helps developers focus on smart prevention and targeted testing, making multi-threaded programs more reliable and easier to debug.